In this video, I'll talk about the addition reactions of aldehydes and ketones when the nucleophile is actually a nitrogen base atom. And we will be making an imine, enamine, oxime, and a hydrazone. So I will talk about those along with the mechanism, but just before we dive into the reaction mechanisms, let's just talk about what imine, enamine, oxime, and hydrazone looks like. So this is what the structure of imine looks like, where you have a carbon-nitrogen double bond, and typically imines are retrieved or synthesized when you react aldehyde or a ketone with a primary amine. And then the same time, if you have a secondary amine, then the reaction with aldehyde or ketone of secondary amine will make an enamine. To make oxime, you would need something called an hydroxylamine as your reactant along with aldehyde or ketone, and to make hydrazone you will be needing hydrazine as your reactant along with aldehydes and ketones. Now all these reactions are actually done under acidic conditions, and also keep in mind all these reactions are reversible, which means I can go ahead and hydrolyze any of these amines, enamine, oxime, hydrazone derivatives back to the ketones and aldehyde under acidic condition along with water. So when you're doing hydrolysis, obviously you're going to be throwing a lot of water, but you have to have hydrolysis done under acidic or basic conditions. Now, the hydrolysis of these derivatives only done under acidic conditions. They're fairly stable under basic conditions. And also keep in mind they're actually made under acidic condition as well. Now let me talk about in a very first one where I'm making it an amine. So this is going to be an acid catalyzed with an aldehyde or ketone with a primary amine. So I got this primary amine here. I'm going to be using catalytic sulfuric acid or sulfonic acid here. Any of the acids technically work, but just needs to be in catalytic conditions. And then what I'm going to be making at the end of the day is an amine here, which would look like I would have a nitrogen here, and I could possibly make both cis and trans, but if I want to say which one is going to be more stable, yes, the trans or E configuration would be more stable. And then you make water along with it. Now, where that water is actually really coming from, so that's a question that you want to ask yourself. So it is combining those two things, kind of condensation reaction. So this is going to be making water. So I have the oxygen coming from this ketone or aldehyde, and I got these two hydrogens kind of coming from here from the amine, and that's going to make the water. Now, like I said, this reaction is indeed going to be a reversible reaction, which means I could technically go back to make the starting material if I use a lot of water with acidic conditions. So this is kind of a reversible you can think of as an Lee-Shetler principle. If you don't have a lot of water, it's going to shift the reaction to the right side, but if you have a lot of water, it's going to shift the reaction to the left side. So you can go both ways back and forth on these reactions. I do have a structure of a sulfonic acid made here, so it's just basically the proton that you're getting from the sulfonic acid, or TSOH, and like I said, you can also use sulfuric acid. Now if you have a little bit of sulfuric acid in there, there's a good chance that you may have a little bit of this amine protonated. You're not going to have all of it protonated because you're not using a lot of acid. So I can just say H2SO4 is going to be used up to protonate that. And this is not really the structure of H2SO4, but it's just going to go back onto that oxygen, and you ended up making NH3 plus, and you got HSO4 1 minus. Now I can certainly use this guy as my starting material here to go ahead and start the reaction with an aldehyde or ketone, but sometimes you can also just use directly from the sulfuric acid. So that since this is done under acidic condition, if you recall, the very first thing you want to do under acidic condition is to go ahead and protonate your oxygen on that aldehyde or ketone. So I want to go ahead and protonate that oxygen using the protonated amine that I just got. And like I said, you don't necessarily have to use protonated amine, but that's just the most common thing that you would see. You could also use sulfuric acid here directly to go ahead and protonate this oxygen, so that's completely okay as well. I want to go ahead and go use this oxygen here to go and protonate this. Get a positive charge, and then you obviously have the amine kind of left behind here. So in the second step, what I can do is I can go ahead and do the nucleophilic attack here. Makes this more electrophilic because of the positive charge on that oxygen. This breaks up here, and you ended up getting, I'm just going to copy that here. The hydrogen is still there. You make a new bond here with the remaining stuff. So I got nitrogen with 2 hydrogens, and you got 2 R groups there with a positive charge. And then I want to go ahead and retrieve the acid back. So in order for me to retrieve the acid back, I could go ahead and use HSO4 1 minus here, but you can also use just the amine that you have left behind in there, because you're not going to be using all the amine all together. That's another thing you want to keep in mind. So you can use this, or also I can use HSO4 1 minus. Either way, it's fine. So I want to go ahead and grab this proton here. Okay, so that makes this right there. And remember, I want to actually go ahead and lose the water here, because this is what we're going to be doing. So to lose the water, I can run another proton transfer reaction, and I can certainly use the protonated amine here. And if you don't use the protonated amine here, I could use sulfuric acid. Like suppose if you use HSO4 1 minus here to grab this proton, then mechanistically I would have H2SO4 made here. The H2SO4 here would be used up to protonate this oxygen. In this particular case, in this diagram, I'm using the amine. Now, which one is really true? Both of them are actually really good. I mean, you can use mechanistically both of them, but if I want to look at what exactly happened in the solutions, it's probably the amine that's really doing the job, because it's not it's more basic than the HSO4 1 minus. So going back and forth with the protonation and deprotonation. So then I want to go ahead and protonate this oxygen here again. And when I go and protonate this oxygen, I'm going to go ahead and get so remember there was actually 2 lone pairs here. So get a positive charge. Now that's a good leaving group. So since that's a good leaving group, I want to go ahead and get rid of that. And to kind of knock that water out, I'm going to be going ahead and using this lone pair on that nitrogen to kind of go ahead and knock in there. And then that gets knocked out. So I ended up getting something like this. I'm just going to copy this down here. I'll get this right there. Make this a little bit smaller actually. And remember, I still have the hydrogen on that nitrogen there, so this gets a positive charge. And you have kind of lost the water there. And then eventually I want to go ahead and get rid of that proton. And here I can again use the amine, or I can just use the HSO4 1 minus. Now you may wonder why I want to use HSO4 1 minus here. Well, we're about to complete the reaction, so I want to make sure I retrieve my acid back, or I show that I'm retrieving my acid back. So I want to go ahead and grab this proton using the HSO4 1 minus. But like I said, if you use the amine here, that's completely okay as well. And that would make your final product here. That would be this. And then you also already have water kind of produced. So this is what an amine is going to look like. So then if I have a secondary then how the thing's gonna look slightly different here. So again, I can go ahead and use this guy here, and I can go ahead and use H2SO4, or even I can use TSOH depending on what acid I'm really using here. I'm going to go ahead and protonate this, and I can use that protonated amine to run any acid-base reactions down the line. So this, go ahead and grab this proton here, this comes out here, get TSO minus. I can go ahead and retrieve that TSOH at the end of the day, but I can certainly use this protonated amine here and unprotonated amine to run any acid-base reactions here. So then again, the first reaction that I want to use is to protonate that oxygen on that ketone. So to go ahead and use this right there. So we'll have this proton grabbed, this coming down here. So that would make, after protonating this oxygen, I would have carbon more electrophilic. So that means I'm going to be using that amine now to do the nucleophilic attack. So remember, this is a secondary amine where it's got only one proton on it. So this does the attack right there. This comes out. So let's see what that makes. I'm just going to go ahead and copy this down. Got another lone pair here, so now I'm going to have, okay, I'm going to go and make a new bond here, so I'm going to show that with green color. And then I got N, and I got two hydrogen, two R groups. And those R groups could be the same, could be different, as it doesn't really matter. So then, that one, you have it there. And then the next step, I want to go ahead and run an acid-base reaction here, a proton transfer. So again, to run the proton transfer here, I can certainly use just another molecule of our amine. And if you don't want to use an amine, I can just also use TSO minus in this particular case. But since I want to be doing all the proton transfers with the protonated amine or just a regular amine, we'll just use that here. So that will remove that proton. And now I get a lone pair on that nitrogen there. And obviously I got a molecule of protonated amine kind of shown up here. Now don't get confused with like, where am I getting that amine from to protonate this? Remember, this is all in solution. You're not going to have one molecule of ketone and one molecule of amine. You're going to have just thousands of molecules of this, and when you're running the mechanism, you can just use those back and forth. So then again, I want to make sure I get this OH removed here, but the OH is not a good leaving group under acidic condition. I got to make this oxygen protonated. So that's the next step I want to do. I want to go ahead and protonate this oxygen. And again, I want to be using that protonated amine to just run the proton transfer here. So I'll use one lone pair. I still have the other lone pair still in here. And I have this protonated now with a positive charge. Okay. And then obviously that, if you want to keep track of all your reactants and everything, that would have just a regular amine kind of sitting in here. Now this is a good leaving group. I can go ahead and knock that out. So I want to go ahead and use the lone pair on that nitrogen to kind of go and create the pi bond here, and as a result the water leaves. So I lose water here. And then I make this double bond, a new double bond I can say. and the nitrogen with a positive charge. And then I obviously lost the water here. So now, if you look at the difference between this product here that you made after reacting with secondary amine, and let's go back here with this product here when we had done this with primary amine. With the primary amine, I still have one proton left here. So what we did, we just used HSO4 1 minus, or I could have also have used just a regular amine, or I could mechanistically, I could have just used water as well to just go ahead and grab that proton. So it doesn't really matter. As long as you have any base in the solution, any conjugate base in the solution, you can use those mechanistically. So I was able to grab this proton, and that's how you made a carbon-nitrogen double bond. But then with this secondary amine, the problem is I don't really have any proton left on this nitrogen, so I don't can't really remove anything from that nitrogen. And this is where it changes slightly. So I don't want to be leaving the positive charge on that nitrogen. So then the question would be, okay, where am I going to be losing the proton from? And then I can certainly use TSO 1 minus here, or even I can use water here to just kind of show the acid-base reaction or proton transfer reaction. I want to be using the proton on that adjacent carbon. So because I don't really have anywhere else to go to get the proton, so I want to be using that proton to grab that, to get rid of the positive charge on that nitrogen. So it grabs that proton, this bond goes in there to create the double bond, and then this pi bond breaks and goes on to the nitrogen to restore the electron density at the end of the day. So I'll end up making got only one bond here, that, and then I obviously created a pi bond right there. So that's what your enamine is. So if I want to say what the product's going to be, this is going to be your product or one of the products when you run this, and you're also going to be making water along with it. So like I said, these reactions are reversible. So if I'm using just the catalyst, acid catalyst, no water at all with an enamine, then it will go forward to make this enamine and release the water. But if I run this reaction, or if I have this enamine produced here, and if I want to make sure it goes back, I can go ahead and hydrolyze this under acidic condition, but I will just use a lot of water in this case. So because when I'm using a lot of water, it's going to shift the equilibrium to the reactant side, and this will end up making it in a ketone and in a secondary amine here. So I don't know why this is drawn twice here. Okay, so this is what it's going to look like for the enamine synthesis. Now, for your oxime synthesis, this is not that complicated. It's going to be very similar to actually the primary amine stuff. So what I'm really going to have at the end of the day is this right there, and I would have a double bond with a nitrogen, and then I would have an OH. So I want to go ahead and make, possibly this is a trans, because that's probably going to be more stable than the cis form. And then I would have water kind of released. So where that water is coming from, well, I can say the oxygen here and the H2 here is really the one that's getting the water in here. So the mechanism is actually going to be very similar. So you may want to actually try it and see if it matches with what I got here. So the first thing I want to do is go ahead and protonate this NH2OH. So I got NH2OH with, let's say, H2SO4. And this is what the structure of H2SO4 looks like if you ever wonder. So I want to go ahead and grab this proton here. And then I make NH3OH plus here and HSO4 1 minus. So I will use this protonated oxime here to run any proton transfer reactions. And like I said, if you don't want to use that, you can just directly use sulfuric acid or whatever acid that you're using here. Sometimes you probably just say H plus, so then you can just use H plus in that case. And so the first reaction would be I want to go ahead and use that oxime here to go ahead and protonate this oxygen. So I get this hydrogen installed here. This gets a positive charge. And now I got this oxime here. I'm just going to put the hydrogens together. So now that carbon is more electrophilic because oxygen has a positive charge. So we go ahead and use this lone pair to attack this carbonyl carbon here. And then this comes out here. Okay, I'm going to go ahead and break this. So now I got two lone pairs on that oxygen. Make a new bond here with the oxime, with the hydroxylamine molecule. So far it's very similar. With the really difference with the primary amine is that you have an R group in primary amine, and here you have an OH. But then other than that is kind of pretty similar. And then I want to go ahead and run a proton transfer here. So to run a proton transfer, I can use any conjugate base, including HSO4 1-. But let me just go ahead and use oxime here. I mean hydroxylamine here. So to be consistent. So like I said, you can use anything, any conjugate base. So this actually makes that. And then I have OH there, and then I'm going to go ahead and protonate that oxygen because I want to get rid of that OH group. So to protonate this, I want to go ahead and use, grab this proton here. That you make NH2OH back. And I can go ahead and get rid of this. I want to go ahead and use this lone pairs. Very similar mechanisms with the rest of them. And then this gets knocked out. Now I go ahead and make something that kind of looks similar to oxime, but not quite there yet. Still have an hydrogen there. I want to put the OH there because I want to make a trans instead of cis there. Positive, and I have lost the water here. So I want to go. The last thing I want to do is just deprotonate that nitrogen. And like I said, you can use any of the conjugate bases. I can use, let's say, HSO4 1- here, or I can use H2O here, or I can use NH2OH just to remove that proton. It doesn't really matter. It really, to be consistent, like whatever you started using with, I want to kind of go ahead and use that. And then this comes down here. So you make an oxime at the end of the day. So so that's what your products were. You made an oxime, and then you would have water in there. Now this is what the oxime synthesis is going to look like. So now for when I say for the hydrazone synthesis, it's going to be exactly the same, but the difference is instead of having an OH, you have another NH2. So what I do is I would have an NH2 in the first step getting protonated depending on whatever acid I'm using here. So let's say I'm using sulfonic acid here, TSOH. So this is actually written together here, just an abbreviation, not the structure. So this grabs this proton and this comes down here. So now you have NH2, NH3 plus, and then TSO minus. So then what I want to use is this as my acid-base reaction, this as to run any proton transfer reaction. So I'm not going to do this, but what I'm going to do is just copy this down. So just to kind of save the time here, but I recommend you to kind of do this actually. So I want to go ahead and copy this part here, and I'll show you how what's really going to be the difference in here. So exactly right there. So what really difference that you're going to have in here? So instead of an OH2 here, I'm going to have just NH2 here. Because remember, that's what we had made here, NH2, NH3 plus there. So then we run the protonation, and then I would go ahead and change those as we move along. And then you do the nucleophilic attack using the hydrazine there. And then I want to go ahead and probably just copy this here. Okay, let me copy that again. So this is pretty much it's going to look like. So what I got, I'm going to change those is place the NH2 there, NH2 there, really place the NH2 there, NH2 there. I mean, you could have just compared this with the primary amine as well. And an NH2 there and an NH2 there. So this makes it like a hydrazone at the end of the day. So your final product would again be in a condensation reaction where you make a carbon-nitrogen double bond. It's kind of an imine, but since the reason why we call it hydrazone because it got another NH2 group there. And then I would have water kind of removed there. So again, this reaction will be reversible as well.